You're here because you want to master the mole concept and stoichiometry with a University of Cambridge graduate. Let's begin. Before we start, don't forget to go down in the link below so that you can download a copy of the notes for yourself and sit down in the lecture with me as I run through the mole concept and stoichiometry with you. So, the mole concept, filled with calculations and pretty much understanding of how reactions and balancing equations work. I'm here to teach you how to do all of this. So today I'll be mainly running through with you the theories behind the mole concept. As for applications, I'll be posting future videos to show you how I can apply the theories that I'm running through today into the questions that you would face or potentially face in the exams. As usual, I've left a list of learning outcomes below for you, and I'll be referencing to them throughout the whole lecture. So starting things off, what is relative atomic mass? Relative atomic mass is the ratio of weighted average mass of an atom of an element to 1/12 of the mass of a 12 carbon atom. They pretty much use 12 carbon atom because 12 carbon atom was the closest they would ever get to a plain 12 grams. And therefore, it was used as a basis of measuring the atomic mass of every other atom in the periodic table. So for atomic mass, there are questions that do come out that ask about relative abundance. And you just need to know this formula over here. Relative abundance over 100 times the mass of that particular, most of the time it's an isotope, plus the relative abundance over 100 times the mass of the particular isotope. You keep repeating it until you've covered all the isotopes in the question, and this should equal to the AR, which is the atomic mass. So do take note that a question can ask you to calculate the AR, or they can ask you to find the relative abundance of a particular isotope. Either way, just manipulate the equation accordingly. Next, here are some useful equations for your calculations in the mole concept. Pretty straightforward. To start things off, we have the number of particles n 6.02 times 10 to the power of 23. The relationship is 1 mole of any particle is equal to 6.02 times 10 to the power of 23 number of particles. So this can be atoms or molecules, and use it accordingly. How you would use this little triangle over here is that, let's say you're given the number of particles of a particular atom and you needed to find the number of moles. You would just take n equals to the number of particles divided by 6.02 times 10 to the power of 23. Next is, we have mass and we have number of moles and we have molar mass. So the moles, 1 mole of anything times the molar mass, which is the MR or the AR actually, would equal to the mass of the mole. So volume, mole, and molar volume pretty much follow the same as mass and molar mass. And the more commonly asked is N with concentration and the volume. So your concentration is usually in moles per dm cube, which signifies the number of moles of a particle in that 1 dm cube of water or aqueous medium or solvent. Next up is empirical formula. And how you would answer these kind of questions is to draw this table below. So we break down the elements and find out the masses, or the mass in 100 grams, which is pretty much the percentage by mass of a particular element within the molecule, and then find the number of moles. So how you find the number of moles is to divide it by the MR or the AR, more likely the AR, but it could be both. And then you would find the simplest mole ratio. This simplest mole ratio would be the empirical formula. Next up is reactions. So this is a list of very typical reactions that you would commonly encounter within the whole chemistry syllabus. Of course, there are more, but this is a good first step for introducing you to the world of chemistry. So to start things off, we have reactive metals, and when they react with water, because they are reactive, you would get the hydroxide, the metal hydroxide plus H2. You could also have a reactive metal react with an acid, something that you probably touched on in secondary school, and you can get the salt plus hydrogen gas. You could also have hydroxides or oxides, which is pretty much bases, that react with acids, and you can have the acid-base neutralization, which gets salt and water. You can get carbonates, which react with acids, and they give you your salt and carbon dioxide and water. You have ammonium salts that react with bases, one of the more unique reactions because this involves a base. And from this you get salt and ammonia and water. So on to the more not so simplistic reactions that are not really that intuitive. First up, we have precipitation. We always have to start with two aqueous substances, and then you get a solid that comes out of it through the exchange of ions. This is actually a very common reaction, but it's missed out a lot as a potential reaction. And then we have combustion, where you combust a particular molecule in excess oxygen, or perhaps not even excess oxygen, and you will get like CO2 and H2O. And lastly is displacement. So displacement, we are just displacing a less reactive atom or even a cation with a more reactive atom or cation. Next up, we have the reactivity of metals. I'm not gonna spout out all the elements that you should memorize, but you should get a good sensing of the reactivity of metals, as it tells you of the potential reactions that metals can have. For example, we know that copper is lesser in reactivity compared to hydrogen over here. And this clearly shows that copper will not react with acids. And you could say the same thing for silver and gold. Other things to take note are like oxidizing power. So oxidizing power, you have F2 that is greater than Cl2 and so on and so forth. And the way you remember this trend, if you have difficulties memorizing, is that F2 is higher up in the periodic table. And because it's a halogen, it's higher up in the periodic table, it's more electron hungry due to its lower atomic radius, or lower of principal quantum shells. And because of that, since it's more electron hungry, it is more likely to oxidize another substance. And then next up, we also have solubility. So for this solubility table, please, you have to memorize this. You have to memorize this no matter what, because these has applications not only in mole concept, but also in pretty much your foundations of whole of chemistry. For example, in qualitative analysis that you would do subsequently in the labs, you would need to have concepts of solubility, and this pretty much gives you a very good foundation for the rest of the topics. So going down the list, we know that all group 1 and ammonium salts are soluble, all nitrates are soluble. These are the two very big rules. And then you have Cl- and Br-. They are usually soluble except for your Ag and Pb. Your sulfates are usually all soluble except for your Pb, your barium, and your calcium. And starting from the right over here, all your carbonates, your hydroxides, your oxides, they are insoluble. Except if you look to the left, your group 1 and ammonium salts. Because again, group 1 and ammonium salts are king, right? Now just a little note that whenever we do our calculations, you would always have to take note of the limiting reagent, right? A little hint, okay, when trying to spot whether the question is trying to test your awareness of limiting reagents, is that when a question gives you too much information, let's say they give you the number of moles of A and the number of moles of B, both reactants, right? You should already pay attention because most likely one of them is a limiting reagent. Please don't fall for the oldest trick in the book. And then after that, you want to use the limiting reagents number of moles as the base to calculate the moles of your product. And do remember that whatever is in excess, don't just disappear. Don't forget, they're still there in the system. And so questions love to ask whether you're still aware of that excess reagent. Next part is percentage U. So do know this formula where percentage U is equal to the actual mass over the theoretical mass times 100%. And this is usually asked because we know that most substances in the world, for example, your ores, like iron ores, for example, that come up from the caves, they are not 100% pure. And in order to determine the purity or the percentage yield of a reaction, you would need to go through this formula right here. So following up, combustion is a very key topic that loves to be asked by the examiners, and this is because most students forget how to derive this equation over here. CXHY gas plus the amount of O2 giving CO2 and H2O. Usually the questions are phrased such that you don't really know the molecular formula of the hydrocarbon, and only with information from the question, such as the volume of carbon dioxide produced, then you would know the molecular formula of the hydrocarbon. In order to determine this, you first have to write this whole equation, and you can derive it using simple algebra over here. For example, with Cx, you will know that there's X amounts of CO2, and with Y amounts of H's, you will know that there is Y over 2 amounts of H2O. And from these two values, you can back calculate and find out the amount of O2 required. Next up, you will need to draw a ICF table. ICF stands for initial, change, and final volumes or concentrations. So by drawing this, it would be very easy to track down the changes of reactants into the products. And this will also give you a hint as to whether there are any excess reagents or not. Lastly, do take note that H2O usually comes in a liquid. But in high combustion temperatures, you would get a gas. So depending on the question, they will usually tell you whether it's room temperature or not really room temperature. And there you can tell whether H2O is a liquid or a gas. Do take note that this information does come very crucial usually for combustion questions. Alright, following up is volumetric analysis. And here, we mainly talk about titration. So for titration, there are a few key terms that you need to know. One is equivalence point, which is when the reactants have reacted just nicely with each other. And you can usually tell from the color change in the indicator, which brings me to my next point, the endpoint. And the endpoint is indicators and the titration just changing the color. Usually the endpoint, you want the endpoint to be almost as close to the equivalence point as possible. So here are a list of common pH indicators that are used for titration, and I would memorize at least the first two because they are the more common indicators that are used. On to the next mini segment, we have dilution. Just take note that C stands for concentration and V stands for volume. So whenever I increase my volume, it would directly affect my concentration, and vice versa. So whenever I'm doing dilution, this formula could be very useful in your calculations. Next is redox reactions. Redox reactions comprise of oxidation and reduction, and these two reactions are pretty much new in your syllabus. So how you classify oxidation and reduction is according to this table below. In oxidation, you do have a gain of oxygen, which is pretty self-explanatory, and in reduction you have a loss because they're the opposite, or in reduction you have a gain of hydrogen, but in oxidation you lose. And then in oxidation you lose electrons. How you memorize this is ole, and reduction is just the opposite. And another key way of finding whether it's oxidation or not is looking at the oxidation number. If there's a gain in oxidation number, it's oxidation. If there's a loss or a decrease in oxidation number, if there's a decrease in oxidation number, it would be reduction. So how do I calculate oxidation number? Just know that oxidation state is the hypothetical charge of your atom if all the bonds were treated as ionic. So here's a little example for you. When I look at sodium nitrate, for example, I will go with the atoms first that are very easy to determine the oxidation state. There are some simple rules. So for example, oxygen tends to be -2 and H tends to be +1. Although not always the case, but this is a good rule of thumb to have. So if I look at this, my oxygen tends to be 3 times -2, which is -6 from all the oxygen in total. And then sodium is definitely +1 because it is a group 1 atom. And therefore, because of that, you can calculate from this, in order to make the whole charge neutral for sodium nitrate, my N has to be +5. Now, what are some common oxidizing agents and reducing agents? Oxidizing agents that are very common are, for example, my potassium dichromate 6 to give Cr3+, my manganate, right? And also hydrogen peroxide. And what are some common reducing agents? They're like your thiosulfate. This is very commonly asked, especially in your iodine clog reactions. Do take note for like future topics, right? And also your hydrogen peroxide. Just a key little note that this proportionation is actually your redox reaction where one species is simultaneously oxidized and reduced. Do memorize this definition. I don't know why exams love to test this, but they love to rip a mark off students who don't study, I guess. And lastly, you need to know how to balance your redox/half equations. So here are the following steps. Just follow all these and you'll definitely be able to balance them. First, you have to balance all the atoms other than H and O. And then second, you have to balance the number of O by adding H2O to the other side. And then you have to balance the number of H's by adding H+. And then overall, looking at the charge on the left and the right side of the equation, you have to add electrons to balance the charges. Once you've done that for both half equations, do multiply the half equations accordingly just to balance the charges between the two half equations. And once you've done that, you can combine both half equations to give the overall equation. And lastly, to take note, if you're tested on a system in an alkaline medium, you have to add the same number of OH- as there is to H+ for both sides of the equation. And from there, you will get H2O because H+ plus OH- on one side will give H2O. From there, you have to cancel out the H2O. And there, you can get your half equation in the alkaline medium. So that's all for the mole concept. As I've said earlier, this is just a theory, and I would strongly advise that you spend some time to go find some practice for yourself in order to get better at the mole concept and stoichiometry. If you like this content, be sure to hit the subscribe button down below so that you can get more frequent updates from this channel. If you want to enroll in my online class, be sure to click on the link below so that you can book a free call with me today. I will do a free run through of your test paper and clarify any difficulties and challenges you might have and show you why this program is the best fit for you. I'll see you in the next video.